We experience the world in 3 dimensions, but the universe and the data that we record about it is much richer than just 3 dimensions. What if you could step outside the limits of visual perception to comprehend structures in dimensions far beyond our natural understanding? Alright. I know that sounds a little dramatic, but it's true. Today, we're talking about dimensionality reduction, a secret technique used by scientists all the time that helps them do things like look inside DNA to help figure out what genes cause cancer, or to help them learn about how the brain encodes information, just to name 2 examples. Hey, welcome to Hyperfixation Sandbox. Here, I take interesting topics and break them down into their basic components to help you understand them without needing a degree in math. By the end of this video, you'll know how to use dimensionality reduction to decode brain activity and use it to predict an animal's location in space, so stick around. But first, we've got to start at the beginning. Before we can reduce dimensions, we have to know what even is a dimension. A dimension is just any kind of measurement. Let's say every day you look outside and you record the temperature. You're actually recording 2 dimensions there, the day and the temperature. Now let's say you get a little bit fancier and you look at wind speed, humidity, and cloud cover. In addition to your first 2 dimensions, you're now recording 5 dimensions of data. And for this example, let's imagine there are only 2 states. It can either be a sunny day or it can be a rainy day. Even though you're recording 5 values, you can just look outside and you can see that it's either a sunny day or a rainy day. So you'd want some method of taking those 5 measurements and condensing it into a single measurement of a rainy day versus a sunny day. This example is a little bit silly because you could always just look outside and get the answer yourself rather than building a complex mathematical model. But there's a lot of systems that you can't just look at that you still want to understand the structure of. That's what dimensionality reduction does. It takes a lot of values and boils it down to a small amount of values by throwing out less important information. How does dimensionality reduction do this? You can think about shining a flashlight at your hand. Your hand is a complicated 3-dimensional object with color and texture and a whole bunch of other stuff that you don't really care about. When you shine your flashlight at your hand, the projection on the wall is a black and white image that you can still recognize as a hand. However, it has a lot less information than your actual 3D hand. The shadow represents the idea of your hand using a lot less information. There are actually a lot of different dimensionality reduction techniques where they're all trying to optimize how to get the most information out of the least amount of data. However, no matter what, you still have to throw something away. Each method decides what is worth keeping and what's worth throwing away. Now that we understand the general concept of dimensionality reduction, I'm going to go through the 4 most popular methods of dimensionality reduction and explain them in a way that you don't need a math degree to understand. And then, using those 4 techniques, I'm going to go through 2 real-world examples and show you what that looks like. First up, we've got principal component analysis, or PCA, which is by far the most famous of the techniques we're going over today. When you do PCA, you're going to find the principal components of the data. Alright, let's imagine that you have some data. We're going to look at this 2D graph just to keep things simple. So you can see that our data follows some type of distribution. If you draw a line through the longest part of that data, congratulations, you just found your first principal component. The only thing you have to do now is find the next longest line through that data that is at 90 degrees to your first data. Because we only have 2 dimensions, you're done. But if you had more dimensions, you would now find a third line that is at a right angle to both the first and the second line, and then another one and another one for all the dimensions of your data. You might have noticed that we haven't reduced any data yet. All we've done is define new axes for the data to exist in. This is actually one of the strengths of PCA. What you have now is an ordered list of dimensions that contain the most information about your data. Why is that important? Because your list is ordered, you can throw away the later dimensions and keep the most important dimensions, representing the majority of information about your data with the fewest number of numbers. Another really great trick about PCA is that you can take that reduced data and you can project it back into real space. This allows you to reconstruct a full approximation of your data just using your reduced values. Our next method is linear discriminant analysis, or LDA. This method requires you to label your data to what group it belongs to, and then it basically finds a line that puts each group of data in timeout. As you can see here, when you have 2 groups, you just get a line right down the middle, and then when you project it down, it'll put each of the groups on either side of the line. You might wonder, what happens if you have more groups? Well, all you do is you just have multiple lines for each group, where each line puts one group in timeout at a time. Now, both PCA and LDA are what we call linear transformations, which just means that we take all the data and we transform and stretch it and rotate it uniformly. Our next 2 methods are nonlinear transformations, and all that means is that different parts of the data might get affected differently than other parts of the data. And this is actually really important because it allows us to capture much more complicated relationships between the data. Our first nonlinear method is t-distributed stochastic neighbor embedding, which is a mouthful. How this one works is you give it a 2-dimensional or 3-dimensional space to work with, and it looks at your data and it finds data points that are similar together, and it just pushes them randomly into this new space. A good way to imagine it is imagine you're sorting laundry, and you kind of want to keep things that are dissimilar far apart from each other. So you put your shirts on one side and you put your socks way on the other side. But then you get to pants. So pants go somewhere in between shorts and socks. And then you get overalls. And I guess overalls are going to go somewhere between your pants and your shirts. And then, okay, now you've got a tank top. I guess that goes next to your shirts. And then you got long socks, and the long socks are going to go right next to your normal socks. And then you get... And so as you fill out this space, the things that are closely related to each other are going to be next to each other, but where they are in this spread out area of your house doesn't really represent anything in the real world anymore, because you just put things that are similar to each other next to each other. Our final method is the uniform manifold approximation and projection method. The way UMAP works is by trying to fit a complicated surface to your data. You can imagine crinkling a piece of paper or stretching a balloon. The goal of stretching this surface is to have each point uniformly distributed away from all the other points. And after you've matched this complicated surface to all your data points, you can stretch out that surface nice and flat, and you have your UMAP representation. But we're done. That's all the techniques. And now that we know the techniques, we can separate them by supervised versus unsupervised, which is just whether the algorithm knows what group the data belongs to or not. We can also separate them by linear transformations and nonlinear transformations, or we could separate them by whether we can reconstruct the original data or not. But now let's get to the fun part of the video and stress test these methods on different types of data. We're going to take this data from 3 dimensions and project it down to 2 dimensions. Now we know that our data comes from multiple different distributions. And so what we're looking for in this transformation is, can the algorithm successfully separate out these different distributions from one another? And we're going to put the projection over here, starting with PCA. With PCA, you can see that it does exactly what it's advertised to do. It found the longest line through the data, and that's going to be through this line here on the x-axis. And then it found the second longest line through the data, that's over here on the y-axis. And then it just smooshed all the data together. Now, you could kind of say that this data is a little bit separated, but it's still fairly mixed. It's just an optimal view through the data. When we look at LDA next, you can see that it does a little bit better of a job of separating these distributions from each other and showing some of that underlying structure of the data, that it comes from 5 unique distributions. Next, when we move to our nonlinear transformations, you'll notice that the style of the graph is very different. Here, looking at t-SNE, you can see that the data doesn't conform to the original shape that it did before. And that's because, like I said, t-SNE is just pushing the data randomly into this new space. But it does do a lot better of a job keeping data points that are similar next to each other. So it does a pretty good job of categorizing these 5 groups. Finally, we're going to look at UMAP. The UMAP graph, similar to the t-SNE graph, is a much more dramatic transformation of the data. It does not do as good a job as t-SNE of cleanly separating the groups, because if I turn this data into black and white, it's really hard to tell which group is supposed to be which other group as cleanly. So that sample data is the most simple case of using dimensionality reduction. Let's sink our teeth into some data that's much more rich. And to do that, I downloaded the MNIST Dataset, which is a really famous dataset in machine learning. The MNIST Dataset consists of 28 by 28 black and white images of handwritten digits. Now, you or I could look at these digits and recognize them as a 0 or a 1 or a 2. But if you're a computer program just looking at the pixel values, how are you supposed to know what's a 1 versus what's a 7 versus what's a 6 or a 0? These are just a list of numbers to you. And so is there any structure underlying these pixels that binds any group of digit with another group? When the MNIST dataset is used in machine learning, usually a lot more processing is done. But we're trying to see how far can we go just with using dimensionality reduction. Now, PCA does a lot better than I thought it would. You can see that each of the digits groups pretty well with similar digits. But you can also see that there's a lot of overlap. 2 dimensions is simply not enough for PCA to find an axis that can separate all the groups, nor is it really trying to do that necessarily. Similarly, with LDA, you just don't have enough space to find lines that cleanly put each group in a corner. There's a lot of overlap here, but Similar to the first example, I would say that LDA does do a better job of trying to separate the data where it can. Now here's where we're going to see the nonlinear algorithms shine. t-SNE does a fantastic job of finding digits that look similar to each other and putting them close together in this low-dimensional space. And you even get some fun information, where you can see where it kind of got the information wrong. Those digits exist in the borders between the groups of digits where it's a little bit not sure where this digit is supposed to go. You can see that these 7s are being mistaken for 1s. These 2s are being mistaken for 7s, and these 6s are being mistaken for 0s. Similar to t-SNE, UMAP does a fantastic job on this dataset. It cleanly separates all the groups from each other, and I would say it keeps them much closer clustered with each other, as well as being more accurate. Alright, for our grand finale, we're going to look at an even more complicated system, a living brain. I've got an open source dataset of the activity of 120 neurons inside a rat's brain as it moves up and down a linear track. Every time a neuron fires, we get a dot here on the chart. Let's see if we can use dimensionality reduction to take this data from 120 dimensions down to 2 dimensions and understand a little bit more about the state of the brain at any given moment. If we take each recording time point as a sample, we can then plot its location in space as a function of time. We can also plot the neural representation of the animal as a function of time. I'm calling the graph based on the animal's location in real space, where orange is the bottom of the track and blue is the top of the track. I'm going to pause for a second and let you watch the whole recording uninterrupted. We've been using PCA since 1901, but still, PCA does a really good job of representing the neural activity in a low-dimensional space. You can roughly approximate where the animal is in this two-dimensional graph, whether it's on the top of the track or the bottom of the track. However, we don't get much more specific information. When you look at our nonlinear transformation methods, we have a much richer understanding of the brain's state at any given point. We can even get the direction. Here you can see the animal is approaching the bottom and then leaving, approaching the top, and then leaving, just using these nonlinear transformation methods. I hope these examples have shown you that dimensionality reduction is an extremely powerful technique that allows you to understand the structure of data that we'd have no chance of understanding on our own. And you can make some pretty amazing visuals while you're at it. If you want to mess around with the code that I use to create these visuals yourself, you can access all the code on my Patreon. I hope you learned something coming on this journey with me. I covered a lot of ground at a really high level. If you have any questions about these methods, feel free to drop them in the comments and I'll answer them as best as I can. I'll also include links to more in-depth resources that you can use to help your understanding grow even further beyond this video. Thanks for watching, and I'll see you in the next one.